Hello, Coach Travis here with another calculus video. So what we got here is we've got the fundamental theorem of calculus, and usually the fundamental theorem of calculus is considered to have two parts, and this one here is what we traditionally call part one. Okay, so you can pause the video and read what this says if you want, but I don't want to worry about what this says right now. We'll come back to it after we've talked a little bit. But what I really want to focus on is this piece of it right here. So the fundamental theorem of calculus part one, it's got this really potentially confusing gadget right here. So well, maybe I will read part of it here. It says, okay, so we start with a continuous function on some interval a to b. So lowercase f is a continuous function on the interval from a to b. And now what we're doing is we're making a new function. We're making a brand new function. And the way we're defining this function is by using this definite integral. So that's not something you've probably ever done before. That is, you've probably never created a function by using an integral, right? I mean, I guess your experience at this point, your experience with integrals is probably, oh yeah, it's the area under the curve, and it's a number. But what we want to do here is we're making a function out of it. So it's not just a number. It's a function. And so this is really at the heart of the fundamental theorem. So if you want to understand the fundamental theorem, you have to start by really understanding this function right here. But this is a very complicated function, or it looks complicated. I mean, it's got all these letters. It's got A's, it's got X's, it's got T's. What the heck is going on with this? This is really confusing. So I want to spend the first part of this video really understanding this function capital F, and then we'll move on to the conclusion. So this by itself is not the fundamental theorem. This is just something that you could do. If you have a function lowercase f, then you can always invent this function here. But you know, that's not a theorem. That's just something you could do. But then the rest of this part, the rest of this is a theorem. That turns out this function has some very interesting properties, and that's the fundamental theorem guarantees that those properties will happen. Okay, so I apologize for going on a little bit long there, but let's kind of investigate this function here. But before we do that, I want to say, yeah, it's a real alphabet soup here with the A's, the X's, and the T's. So the idea is I don't want you to freak out about A, because A is presumably just a constant. So A is just a constant, and it can be any constant that is in the domain of lowercase f. So A is presumed to just be a constant number. So that's no big deal. But then the X's and T's, I know, can be kind of confusing. So the idea is the T is what we call a dummy variable. So the T actually is kind of, the way I think about it is it's just a placeholder. So for example, if I wanted to find, I could ask you to find, say, the area under the curve x to the fourth from 0 to 1. So so the way we would write that down as an integral is we would write the integral from 0 to 1 of x to the fourth dx. But the idea is the x there, the x is just representing the variable of integration. So I could just as easily write the integral from 0 to 1 of t to the 4th dt. And those would be the same thing, right? It's the usual thing, like it doesn't really matter whether you call your independent variable x, or whether you call it t, or whether you call it u, as long as you're consistent. And now we usually use x to represent the independent variable because we think about the x-axis and the y-axis. But I can't use, the issue here is I want to preserve that tradition. I want to keep x as my independent variable. But if I want to keep x as the independent variable for this function capital F, then I can't use an x inside of my integral, because then I would end up, if I tried to use the x in both places, I would have the integral from a to x of f of x dx. And the idea is that x, you're supposed to be able to replace x with a constant, right? Like I want to know, like, what's f of 3? So I would pretend that x is 3. But if you put 3 everywhere you see an x here, then you'd get the integral from a to 3 of f of 3 d3, which doesn't even make any sense. So that's why we have to introduce the variable t, is so that we can keep x as the independent variable. And so t is kind of just a placeholder. It's just the variable, it's representing the variable of integration, and the point is it's not x because we want to be able to let x be equal to different numbers. And so we can't have x in the integral because then we would get things that don't make sense. All right, so there's that. And okay, so let's look at, so again, these functions are still kind of mysterious. Like, what does this function look like? I mean, I look at this thing and it seems just really mysterious. So let me use GeoGebra to try to shed some light on what this function is. So okay. So what we got here in this picture is the red curve is going to be the graph of lowercase f of x. Okay, so that's what the red curve is. Okay, and so now what I want to try to draw the graph of is I want to try to draw the graph of this new function. And the new function is going to be the integral from, I'm going to say, -1 to x of lowercase f of t dt. So again, don't let the t, like I just got done saying, don't let the t's freak you out. It's the same function, only I'm letting t be the independent variable inside of the integral, so that I can allow x to be the independent variable for the entire function. So we want to know, so this is, the idea is this is a function that if you change the value of x, then that's going to change the value of this function. And let's see how that works. Oh, wait, but before I go on, you might say, well, wait, why'd you pick -1? And the answer is, we'll see later that it doesn't matter. I could pick anything, but the idea was that the lower bound of that integral can be any number that's in the domain of the function. And so -1 is clearly in the domain of lowercase f, so I can make that a negative. I'm just choosing to make that a -1. Like I said, I'll show you later that you can actually make this number anything you want. And certain things will change, but other things won't change. Okay, and the other thing I want to say is you might be wondering, what's the equation of this function? And it's not, that turns out to be not important right now. We don't need, all we need is just some continuous function. And that's what we got here. I don't care what the formula is. It can be whatever it wants to be. It needs to be a continuous function. So, okay. So how is this going to work here? So the idea is, what I do is I put in a value for x, like say, let's experiment. What happens if I make x equal to -1? So if I put -1 into this function, then I'm going to get the integral from -1 to -1 of f of x. Oops, I goofed already. See, it's my natural inclination to write an x there too, but f of t dt. And so what this is, here's a picture of it here. Well, you could think about it, it's the area. It's the area under the f function from -1 to 1. Well, but if the x doesn't change at all, then you've got no area. So the idea is that f of -1 should be equal to 0. So all right, so I'm gonna go ahead and plot that point. I'm going to plot the point -1, 0. So there's the point right there. So what I'm doing now is I'm graphing. I want to try to graph capital F. So I know that when x is negative, when x is -1, then the value of this weird function is 0. So I'll plot the point -1, 0. Okay, well now let's change x. So what if I change x to say 0? So let's put 0 into this function. So if I put 0 into this function, oops, then I'm going to get the integral from -1 to 0. So let's see what that looks like. So the integral from -1 to 0 is going to be that area right there. And GeoGebra tells me that area is about 2.31. So, okay. Uh-oh, wait. These things aren't quite matching up. Is this... I guess it's okay. That needs to go over a little bit, I guess. So the idea is this x, this slider is supposed to drag me, it's supposed to represent the x coordinate of my input. So all right, so when the x coordinate, when I put the number x into this function, then I get about 2.31 out of the function. So this is going to be about 2.31. And okay, so we'll plot that point. I guess I guess it's maybe right about there. So when x is 0, the y coordinate is 2.31. And now we can just keep doing this. So what if let's just try one more to make sure we got the hang of it. Let's change this to say a 2. So f of 2 is going to be the integral from -1 to 2 of f. And so let's drag the slider out here until we get to about 2. And you can see then GeoGebra tells us that the area under the curve is about 8.97. So all right, so this is about 8.97. All right, so when x is 2, the output of that function is just about 9, which puts it right about there. So I could keep doing this, all night, and it could take a while, but what I can do with GeoGebra is I can have GeoGebra do it a lot faster for me. So what I'm going to do is I'm going to plot points. So you can see that this point right here is exactly the point I just drew. And then I've got the trace function turned on. So as I drag x around, we're going to trace out a whole bunch of the points. So what GeoGebra is doing is it's doing exactly what we were doing down here, only it's doing it a lot faster. So what's happening is this if you think about it, what this function is this is like an area function. So that's what this function has a name. So this is often called an accumulation function. Uh-oh, does accumulation have two C's in it? I sure hope it does. This is sometimes called an accumulation function. But I like to think about it, the way I think about it is I think about it as it's like the area so far function. Because the idea is you tell me the x. So for example, you might tell me x is 6. So if you tell me x is 6, then if I put 6 into this function, I'm going to get the area under the curve between -1 and 6. Oh, and when I say area under the curve, I mean technically it's the signed area under the curve, right? Because the definite integral counts area under the x-axis as negative. So it's really the signed area so far. But it's that's close enough, I think. Okay, so the point is now I can at least draw a graph. I can have GeoGebra kind of sketch a graph of what this function looks like. Just by having GeoGebra is able to calculate all of these areas very rapidly, and it's able to draw a picture. Oh, and what's cool about this is it even works in the reverse direction. You can just keep going back. You can go backwards, and you'll also get the function. Although this is a little bit more complicated, and I don't want to talk about it right now, but it still works. So all right. So the point is that this weird thing that shows up in the fundamental theorem of calculus, it's just a function. It really is a bona fide function. Now it's a little bit complicated to define, but who cares? And indeed, this is kind of, if you're wondering what do mathematicians do, one of the things we do is we make up new functions. We put ideas together to make new functions, and then we study those functions. And so this is kind of an interesting way to build a new function. Is you take an old function, so you take like the red function, and then you define this new function by making a definite integral and putting the x inside as one of the limits in the integral. And that gives you a brand new function. So all right, so that's that. So now I hope you understand that this really is a function, and hopefully it's a little bit less mysterious than it was before. But now I want to talk about the actual fundamental theorem of calculus. So let's see here. Okay, so I used a little bit of fancy algebra and calculus to actually find the equation for this dotted line. So I'm going to go ahead and have GeoGebra graph that right now. So now you can see that, okay, here we have this beautiful blue line, that beautiful blue curve that goes through exactly all the points we just found. So don't worry about how I found this blue curve right now, how I found it algebraically. How I found the formula for this curve. You can figure it out for yourself later, or you can come talk to me about it. But I just want to be able to fill it in as a solid curve so I don't have to work with all these dots. So, all right. Wait, okay. Here we go. Okay, so, I still got a couple of dots here. Let's get rid of those. Okay, and I don't need the integral anymore here, so I'll get rid of that. Okay, so what we got here now on this picture is we got two functions. we've got the function f of x in red, and we've got the sort of area so far function, this accumulation function, we have drawn in blue. And so whenever I get a new function, this blue function is a brand new function. So I'm a calculus student, and so whenever I get a new function, I'm curious about the derivative of that blue function. Whenever I get a new function, I'm curious about the derivative of that function. So let's see if we can say anything about let's see what we can say about the derivative of this blue function. So again, I'm just experimenting, I'm just having fun. And again, this is what mathematicians do. We make up new things and then we investigate them. So we made up this new function, capital F, in blue, and now let's investigate it. And one of the things we'll investigate is, well, what's the derivative? Well, okay, so I know that when I'm looking at the derivative, I want to find at peaks and valleys the derivative is going to be equal to 0. So it looks like my derivative is going to be equal to 0 at maybe about like 4.25. It looks like we have a peak right there. And the derivative is also going to be 0 a little bit above 12. So what am I doing? I'm trying to sketch the graph of the derivative function. I'm curious as to what the graph of the derivative of this blue function looks like. And so, okay, so I look at peaks and valleys, and those are places where the derivative is going to be equal to 0. And then let's see, then if I look at this, I see that, okay, well now between this red dot and this red dot, the blue function is increasing. And we know that when the blue function is increasing, then the derivative will be positive. So, all right, so my derivative needs to be positively valued. And in fact, and at the inflection point, that's where where the derivative is going to be at its highest. So the inflection, I don't know where the inflection point is. I'm just going to do my best here. So the function maybe kind of looks something like this. But the point is that all along that region, the derivative is positive. The derivative is above the x-axis because the blue function is increasing. So remember this red function that I'm drawing, is supposed to be the derivative of the blue function. Okay, and now once I get past 4, now the derivative, now the slope, sorry. Once I get past x is equal to 4, then the blue function starts to decrease. And okay, and if the blue function is decreasing, that means the derivative is going to be negatively valued. And so the derivative is going to continue to be negative until a little bit bigger than 12, because at a little bit bigger than 12, the blue function starts to increase again. So the derivative is going to be negative until we get to a little bit above 12, and then the derivative starts to be positive, and so on. And then we can do the same thing in the other direction. We've got here the derivative, here the blue function is decreasing, so that means the derivative should be negative. So, well, actually it should probably, it looks like it's getting more negative, so it should be, it's concave up, so something like that. Okay, so that red function is a very, very rough sketch of the derivative of the blue function. And I hope that made sense. If it didn't, go back and rewind the tape and pause it. before I drew this red function and see if you could draw the derivative of the blue function. And again, my picture isn't perfect because I didn't actually measure the slopes. So I don't actually know if my red function is really all that good. But it gives us the general idea. Because I think we've seen this red function before. Let's see here. Where is it? It's right. It's right. Okay, so I did a pretty bad job. I did a pretty bad job of drawing. So maybe I could, well, but it's too late now. But the point is that doesn't my red function, the one that I drew, it looks a whole lot like the function that we started this whole discussion with. That was the red function that we started this entire discussion with. It looks a lot like the red function that I drew. And so, and that's actually what's correct. Is that so? My red function is actually not quite accurate because I didn't actually measure the slopes. I just kind of eyeballed it. So, but what it turns out is the red function that GeoGebra drew, the red function that we started this whole discussion out with, that is the derivative of the blue function. So that is the derivative of the, and again, so let's see, don't just believe me, let's think about it. So notice what happens when the blue function has a peak, the red function is equal to 0. When the blue function has a valley, the red function is equal to 0. Here's a valley for blue, the red function is equal to 0. And then when the blue function is increasing, the red function is positive. When the blue function is decreasing, then the red function is negative. So the fact of the matter is, and here I'll write it down, the fact of the matter is that red function that we started off with, the red function that we started off with is actually equal to the derivative of this blue function. And at this point, and that's this blue accumulation function down here. And so this is a whole lot to take in. So maybe, if don't feel bad if you need to go back and watch this video again. I think that would probably be an excellent idea. But this fact right here that we observed by drawing these pictures, this is the fundamental theorem of calculus part 1. So here's the way I think about it. The way I think about it is that this is kind of saying that derivatives and I pointed the wrong things. That derivatives and integrals are inverse operations. Because what did we do? Let's think about what happened. Let me bring up some white paper here so I can write. Do I have some white space here? Yeah, I guess I have a little bit. So, because what did we do here? What we did was we started with the function f of x. And then we created a new function. We created this new accumulation function. We said, so this was, yeah, and what we did was we integrated. We did the integral, we integrated. So we did the integral from -1 to x of f of t dt. So we took the original function and we built a new function by putting it inside of an integral. And then, what did we do? Then we found the derivative. So we found the derivative of this function, And when you find the derivative, we just got back to where we started. That's the whole process here. So this is what we mean when mathematicians or when your calculus teachers say derivatives and integrals are inverse operations. This is what they're referring to. So if you start with a nice continuous function and you kind of apply the integral to it to get a new function, and then you find the derivative of that new function, then you're just back to where you started. And that is exactly what the fundamental theorem of calculus says right here. So let's read it now that we've seen all the pictures. Let's read the words ourselves here, and then maybe refer back to the pictures when we need to. So we start with a continuous function f of x. So that was the red function. And then from scratch, we built this new function. And this was like the area, this was what we called the accumulation function, or the area so far function. So again, this is really a strange gadget, but hopefully this video sheds some light on it. So now you have this new weirdo function, and it turns out that function is nice and differentiable, and when you find the derivative of it, you get the function that we started the whole process with. You just get back to where you started. That is the fundamental theorem of calculus, part 1. And again, it's kind of an amazing fact, because again, if you think about how we built this function, this was a really strange function. This was really weird. Building this function was kind of a lot of work. And so we might have thought, oh, well, there's this who knows what the derivative of this function is. It's too crazy. But it turns out it's not crazy at all. It's just the function that you started off with.